Oh, hello. I will be doing a few examples on this new topic, linearization, today. This is section 3.103, section 10, chapter 3 of your textbook. Okay. This is on, okay, the section is on linearization and the differentials. Okay, I'll talk a little bit about the differentials when we come back to class. Okay. We're just going to focus on linearization now. Okay, so what we're going to have is we have a function that is differentiable at a point A. So I will give you just a formula and give you an example before I explain to you what that linearization is, and I'll explain to you what it is. Okay, suppose a function is differentiable at A. So a function f is differentiable at A. Okay, I'm just going to give it a name, y equals f of x. Okay, so here's a function, y equals f of x, and here's a point A, and it's differentiable at A. We can find the derivative of the function. So the idea is we're going to create a new function. We'll create a new function, linear function. Just like y equals mx plus b kind of linear function. This new function is, we're going to call it L of x. And the formula is first compute the functional value of f at A, which is really this point, A f of A. So the y value at A. And take the derivative of the function, compute at A, and multiply it by x minus A. And this is what linearization is. And I will briefly explain. Let me give you an example first, and then I'll explain to you what this is. Okay, so I'll come back to this page in a second to explain what it is. So an example, I have find the linearization of the function f of x equals x squared at A equals 1. So remember the linearization formula. It is L of x is f of A plus f prime of A times x minus A. That's the linearization formula. So I'm trying to work out to get to this point. So the function f of x is x squared. The value A is 1. So first thing to do is simply compute f of A. Okay. In this case, f of 1, which is 1 squared, 1. Save that for this spot. Okay. Then second thing to do is compute the derivative of the function. In this case, it's 2x. Then compute the derivative at A. That's 2 times 1, which equals 2. Then put all of these together. So L of x is f of A plus f prime of A times x minus A. In this case, L of x is f of A, which is 1, plus f prime of A is 2, x minus 1. We don't simplify this, just leave it like this. That's the final answer. Okay? We don't simplify and get it in the form of mx plus b. Okay? We just don't. So that's the final answer. There is a reason for that. I'll show you. We'll see that when we see an example with a little bit more expansion to it. Okay, basically this is what this is. So the slope of this function is 2, which is 2, which is the derivative of the point, the derivative of f at 1. That's the slope of this function. So what we've just done is simply we found, so in the earlier sections, we calculated the equation of the tangent line at that point. Let me change pencil, change color. Equation of the tangent line, if we were going to do the equation of the tangent line, okay, the slope of this equation is f prime of a. So if we do y equals m times x minus x1 plus y1, what we would have is that y equals m is f prime of a. Okay, I'll put that f prime of a times x minus x1 is a, and plus y1 is f of a. So basically what we have done here is simply rewrote this. That's what we have. So a linearization is essentially the linear approximation to the graph of the function, or the tangent line to the graph of the function. It's a new function. We call it a new function, basically the same tangent line, and we wrote it as L of x to indicate that it is a new function. Okay, but it is a linear function that's a tangent line, and we call it, this is basically the best linear approximation to the graph of y equals f of x. So this is the graph of y equals f of x, and this is that tangent line, and around x equals a, if you zoom in, the two look alike. That's the best linear approximation to the graph of the function. So what we did here is we have y equals f of x, which is y equals x squared. The graph of y equals x squared looks like this. This is the graph of y equals x squared. This is my f. This is y equals f of x. And what we just created is a new function passing through this point with a slope of 2. Rise over run is 2. So if you do that, y equals 1 plus 2 times x minus 1, you get this tangent line. So L of x, y equals L of x, which happens to be y equals 1 plus 2 times x minus 1. So what's linearization? It's a fancy way of saying the tangent line at the point a comma f of a. That's what it means. Okay, let's do a few more examples. So let's find the linearization for the function f of x equals the square root of x plus 1 at a equals 3. If the video is going too fast, you can pause it and take a look at it and then continue. Okay, so this was the page for the first example. I found the linearization of a function f of x equals x squared, a kind of simple function at the point 1. This one is a little bit more complicated function, not too complicated, at the point 3. So what are the things that we need? The first thing we need is f of a. This is the square root of 3 plus 1, the square root of 4, that's 2. We save that. The second thing we need is f prime of x. Let's differentiate this function. Use the chain rule. Okay, times 1. The derivative of the inside is 1. Okay, this is equal to 1 over 2 times the square root of x plus 1. Then you calculate f prime of 3. This is 1 over 2 times the square root of 4. This is 1 over 2 times 2, which is 1 over 4. I put square root of 4 because 3 plus 1 is 4. So that's why our f prime of a. So the linearization is f of a plus f prime of a times x minus a. And that's the final answer. Okay? It's kind of simple here. Let's do a third one. We're going to do linearization for the function g of x equals tangent of x at a equals pi over 4. So things we need are g of pi over 4. That's tangent of pi over 4. This is 1. Things we need, the derivative of the function g, the derivative tangent of x is 6 squared of x. So g prime at pi over 4 is 6 squared of pi over 4. Secant of pi over 4 is 1 over cosine of pi over 4. That's 1 over square root of 2. Then 1 over that is square root of 2. So that square root of 2 quantity squared, it comes out to equal 2. So what's then the linearization? That would be f of a, 1, plus f prime of a, 2, times x minus a. Okay? And that's the final answer. That's the final answer. Okay? If you draw the graphs of this function and this function, you can see that there is just a nice clean this is the y-axis, the x-axis, tangent line at the point AF of A. This is y equals L of x, and this is y equals f of x, the cube root of x, the square root of x plus 1. And around this point, around the point 3, you can see the graph of the curve and the linear graph are very close to each other. Okay? So why do we need this? Well, this is just to the useful of this linearization is to find functional values for x's near a. Okay, let me do one example to show that. Okay, I'll do one example to show that. I have f of x, I think I'm on example 4. F of x equals square root of x at a equals 9. To get the linearization, we're gonna need f of 9. That's square root of 9. So I'm gonna save that. And we're gonna need to take the derivative of the function. Derivative of square root of x is 1 over 2 square root of x. So the derivative at 9 is 1 over 2 times the square root of 9. Square root of 9 is 3. So 2 times 3, we get 1 over 6. So the linearization is f of a plus f prime of a times x minus a. That's the linearization. And we are done with the linearization. But let me add a part B to this. So we're going to approximate the square root of 9.1. Okay, I just want to approximate the square root of 9.1 using linearization. So remember, the function f of x is the square root of x. And we want to find the square root of 9.1. Basically, we're trying to find, so we need f of 9.1. That's what square root of 9.1 is. Okay? But we don't have the tool to calculate the square root function. So we will do the second best. So we'll do L of 9.1. 9.1 is close enough to 9. And so we're going to do L of 9.1 to approximate f of 9.1. Okay? So f of 9.1 is what we need. But that's approximately the same as L of 9.1, which is, I'm going to stick 9.1 in for x in the function L. That's 3 plus 1/6 times 9.1 minus 9. This is the number 3 plus 1/6 of 9.1 minus 9 is 0.1. That's 1/10, which is 3 plus 1/60. Because this is 1/10. 1/6 times 1/10 is 1/60. So if you add these two, this gives you 91/60. No, 91. 6 times 3 is 180. 181/60. That's an approximation to what is the square root of 9.1. And one of the reasons, and the main reason why we don't want to simplify this, is we're usually looking for a functional value near a, in this case 9. So had we simplified it to mx plus b, the calculation would have been a little bit longer. But now we didn't simplify. 9.1 minus 9 happens to equal 0.1. And working with that simple number is much closer. Okay, so this will be the last example that I want to do today. I will come back to a few more examples when we get back to class after the break. As a quiz, okay, find linearization for f of x equals x cubed plus 1 at a equals 1. Okay, find linearization. I will set up a Dropbox for you on Moodle so you can work out this problem and drop it off on Moodle. Have a nice break. I will see you on Monday when we come back.